Hello friends, this is Dr. V. Sivanagaraju, Associate Professor in AC Department, IARE. Today our topic is generation of SSB wave. In previous class we discussed what is SSB and how to describe the in frequency domain and time domain. So in both descriptions we discussed in the last video. So in this video we are going to discuss how to generate SSB wave, single sideband wave. Okay, let's enter the topic. So generation of SSB wave. So here we use two methods. One is a frequency discrimination method and another is a phase discrimination method. So we are going to generate a SSB wave, single sideband wave. So first to take a frequency discrimination method. A frequency discrimination method can be used for generating the SSB modulated wave of the message signal satisfies the two conditions. So before we are going to use frequency discrimination method, that message signal must satisfy two conditions. So let us see what are the two conditions. The first condition is the message signal M of t should not have any low frequency component. Any low frequency component. And second condition is the highest frequency component W of the message signal M of t is much less than the carrier frequency Fc. So these are the two conditions which is for the message signal for generation of this SSB wave and frequency discrimination method. So this is the block diagram of frequency discrimination method. So here we're having one product modulator and one band pass filter, and then is the local oscillator. So already we discussed how to generate a DSB-SC wave. The DSB-SC wave is just a product of M of t and C of t. M of t is the message signal. C of t is the carrier signal. So it is just product of that two waves. We get DSB-SC wave. Now we are going to passing this DSB-SC wave through a band pass filter. So the output of this band pass filter is SSB wave. That means the band pass filter which is going to cut or eliminate one sideband. One sideband. So the output of this band pass filter is just SSB single sideband. Now the band pass filter will pass only one sideband and produce the SSB wave. Now what is the design of this band pass filter? So here we are take care about this band pass filter design. So the first point is the pass band of the filter occupies the same frequency range as the spectrum of the desired SSB modulated wave. And the second one is the width of the guard band which separates the pass band from stop band be twice the lowest frequency component of the message signal. So here is a guard band. So what is guard band? So it is going to separate separates the pass band from the stop band. So these are the design requirements of the band pass filter. So this frequency discrimination method is very easy method for generation of SSB wave. Next, we are going to see the phase discrimination method. Next, we can see the phase discrimination method. So in this phase discrimination method, we're having two product modulators and one summer and 90 degrees phase shifters all that. So in this phase discrimination, we can call as the upper channel having the upper channel also called as in phase channel, and the lower channel also called as quadrature channel. So let us first see in the upper channel having a signal, message signal M of t, which is given as AM cos 2 pi FM of t. That is our message signal M of t, which is given one input to the product modulator and another one would be given as the carrier signal C of t. That is AC cos 2 pi FCT. So the output of the product modulator is one DSB signal. Yes or no? Yes. Just the product modulator, we're giving two inputs. One is a message signal and another is carrier signal. So the output of the product modulator is DSB SC signal. Again in the lower part, we taken as a quadrature. So again the message signal is 90 degrees phase shift changes. Again the carrier signal is also phase shift changes. So both is converted into sine form, sine waves. It is AM cos 2 pi FMT to AM sine 2 pi FMT. Again AC cos 2 pi FCT is changes to AC sine 2 pi FCT. So these two is given to the product modulator. That is in the lower channel or the quadrature channel. Finally, these two outputs S1 of t and S2 of t, which is going to applied to the summer. The final output is S of t. So this is the operation what was going on in phase discrimination. So the output of product modulator I, it is in phase channel, is S I of t, which is equal to M of t is AC cos 2 pi FCT. And the lower channel or the quadrature channel, so the output of product modulator Q is S2 of t M cap of t AC cos 2 pi FCT. So these two signals are fed to a summer. There is a window sending the summer signal. So the output of the summer signal is S of t, which is equal to S I of t plus or minus SQ of t. So the final S of t, the output of the summer is the output S of t, which is equal to AC M of t cos 2 pi FCT plus or minus AC M cap of t sin 2 pi FCT. So here M cap, it is coming from the Hilbert transform. Already in the time domain description, we can see that complex envelope of that low pass filter. Why our band pass filter is changed into low pass filter are taken as an equivalent frequency response of that low pass filter. So finally, we've taken that M cap of t. So there is nothing but Hilbert transform. So that summer output is AC m of t cos 2 pi fct plus or minus AC m cap of t sine 2 pi fct. So the plus sign at the summing junction ALS and SSB with only the LSB. So here the output indicates either one band, that is either upper band or lower side band. So that's why the summer gives S of t, that is the first component plus or minus another component. So the plus sign is coming, we can treat it as LSB, lower side band. So SL of t, which is equal to AC m of t cos 2 pi fct plus AC m cap of t sine 2 pi fct. Similarly, the minus sign at the summing junction yields an SSB with only the USB, that is upper side band. So SU of t is coming when the minus sign is coming. So AC m of t cos 2 pi fct minus AC m cap of t sine 2 pi fct. So these are the methods how to generate SSB. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.